Alright, so y'all have seen by now a handful of examples of integrals or antiderivatives. I want to show you a couple more that I think will be helpful to you on your homework. Before I show you these integrals over on the right, let's review some derivatives. So over here on the left, the derivative of e to the 7x. This is a really basic chain rule derivative. We've got e raised to some power other than just a plain old x. So when we take the derivative of this, we first leave that inside function alone, that 7x, you leave it there, but then you multiply by the derivative of the inside function, right? The derivative of the inside function is 7. All right, so this is just a chain rule derivative. The second example is basically the same, the derivative of sine 3x. Here we have an inside function 3x. So the derivative, you do cosine and then leave the inside function alone, and then multiply by the derivative of the inside function. In this case, the derivative of 3x is 3. All right, so let's keep that chain rule in mind when we do these antiderivatives over on the right. So the integral of 7x dx, the integral of e to the 7x dx. If we think about our basic derivatives, we can kind of guess what the antiderivative here will look like. It's probably going to look something like e to the 7x. And don't forget we need a plus c on this. But just like with our derivative, we need some way of compensating for that 7 that shows up. All right, so if I stop right now, this answer is not going to be right because what we just saw a second ago, the derivative of this is 7e to the 7x. But we don't want 7e to the 7x, we just want e to the 7x. So we need to compensate for that 7 in some way. And it makes sense for an antiderivative, you'll compensate for it in basically the opposite way of how you handled it with the derivative. With the derivative, we multiplied by 7. Here we'll compensate for it by multiplying by the reciprocal, 1/7. You can double check this pretty easily, right? Take the derivative of this function. If I take the derivative, this is how we check antiderivatives. Take the derivative of your answer and you should get back what you started with inside the integral. If I take the derivative of 1/7 e to the 7x plus c, I would get 1/7 e to the 7x times 7, just like we talked about a second ago. And then plus the derivative of a constant is 0. And now the 1/7 times 7 will cancel and give you e to the 7x, which is exactly what we started with inside the integral, so everything works out right. Okay, so whenever you're doing antiderivatives and you have some extra constant being attached to x inside your function, the way you compensate for it in your antiderivative is throw on the reciprocal of that constant in front of your answer. Another simple example, we know that the antiderivative of cosine is sine because the derivative of sine is cosine, right? So here let's do the same thing. The antiderivative of cosine of 3x will be sine of 3x plus c, but we have to compensate for that 3 inside the sine function. We compensate for it by throwing on a 1/3 in front of our answer. Again, double check your work real quick. It's pretty easy to see based on what we have written over on the left. If I take the derivative of my answer, I'll get back the function that I started with inside the integral. All right, so that's the basic idea here that I want to show you. You'll have this showing up in your homework. You'll have your basic antiderivatives that you'll be doing, but some of them will have extra constants attached to the function. And when that happens, we compensate for it by throwing on the reciprocal of that constant in our answer. All right, now on the next page, I'll just give you a couple more to practice on your own, just to make sure you understand the concept. Now, before we do these examples, let me just mention that these are kind of a precursor to an idea that we'll see soon called integration with the substitution technique or U substitution. On these, we're just kind of ignoring that technique because it's kind of the most simple version of it, where we don't really need to go through all the extra steps that we'll be talking about soon. But in all these cases, we've got some extra number being multiplied by x inside the function. So here that extra number is 10, here that extra number is 1/4, and then down here that extra number is 5. So all of these can be handled in basically the same way. Now, if we have something other than just an extra number being attached to the x, like if I have something maybe a little bit more elaborate than just a constant being multiplied by x, then we'll need to talk about different techniques for handling that, okay? But here, all you need to worry about right now is just this simple scenario where you just have a constant being attached to the x inside the function. One thing I'll mention on this first example is another nice little integral technique. This was mentioned in one of the videos that you've already watched. Whenever you see a constant multiple outside of your function, not inside but outside of the function, whenever you see that, one of your properties of integrals is that you can factor that outside of the integral, bring it outside of the integral, and then just focus on what's left. So let's do 9 times the antiderivative of secant squared 10x. So this just simplifies things a little bit, so that the thing that you're working with on the inside of the integral has a little bit less going on. All right, so we don't have to really worry about that 9. Bring that outside of the integral and just attach that to your final answer to this antiderivative of secant squared 10x. All right, so now what I want you to do is pause the video here, see if you can come up with the answer to these 3 antiderivatives based on the basic idea that we saw on the previous slide, and then press play and see if you're able to get them right. Okay, so let's see how you did. On this first one, we have 9 times, the antiderivative of secant squared would be tangent, right? Because the derivative of tangent is secant squared. So I'd have tangent, if this was just secant squared x, I would have tangent x here, but it's not just x, it's a 10x. So I have tangent 10x, and I compensate for that 10 with a 1/10 out front. And don't forget your integration constant, the plus c at the end. So we can write this answer as 9/10 tangent of 10x plus c. And again, double check your answer. You can always check your answer to these antiderivatives by doing the derivative. Take the derivative of this function and you'll get back the function that we started with inside of our original integral. All right, on this next one, the antiderivative of e to the 1/4 x. Again, it's the same idea. The antiderivative of e to the x would be itself. So let's just follow that rule. We'll have an e to the 1/4 x plus c. But we have to compensate for that 1/4 by dividing by it. But if I divide by 1/4, that's the same thing as multiplying by 4. So you tack on a 4 to the front of your answer. This last one, just as a reminder, we know that the derivative of the inverse tangent function, or the arctangent function, however you want to say it, the derivative of arctangent of x is 1 over 1 plus x squared, right? So this is one of our derivatives that we know. And here, notice we're basically going in the opposite direction, but instead of an x squared, we have a 5x squared, right? So this is what we have in this integral. We're doing the antiderivative of 1 over 1 plus 5x squared. So our answer is going to be arctangent, or tangent inverse, of 5x. But again, we compensate for that extra 5 showing up inside my function with a 1/5 out in front. And as always, when you're doing these indefinite integrals, we have to have the plus c attached to our answer. All right, now again, you can double check your answer, take the derivative of this function, and you'll get back exactly the function that we started with inside the integral. All right, so the antiderivative of 1 over 1 plus 5x squared is 1/5 times arctangent of 5x plus c. Hopefully these examples help. So now you should be ready to go on and do the corresponding assignment in MyLab.